Why are temperature intervals not absolute values? Imagine measuring the height of a mountain or the weight of a bag. You need a starting point, a zero, to make sense of the measurement. The same idea applies to temperature. But here's the twist. Not all temperature measurements are created equal. Some scales start at a true physical limit, while others are based on arbitrary points. This difference is why temperature intervals are not the same as absolute values. Let's start with absolute zero, which is the lowest temperature possible. It's the point where particles have the least amount of thermal motion, meaning they're almost completely still. This is not just a random number, it's a fundamental physical limit. Absolute temperature scales like Kelvin and Rankine begin at this 0 point. Kelvin starts at 0 Kelvin, which corresponds to absolute zero, and all temperatures above that are positive numbers. Similarly, Rankine is based on Fahrenheit but shifted so that 0 Rankine equals absolute zero. Because these scales start at a true physical limit, the temperature readings are always zero or positive. Now compare that to relative temperature scales like Celsius and Fahrenheit. These are based on specific reference points that are convenient for everyday life, not fundamental physical limits. For Celsius, 0 degrees is the freezing point of water, and 100 degrees is the boiling point of water at standard atmospheric pressure. For Fahrenheit, 0 degrees was originally based on a mixture of ice, water, and salt, and 32 degrees is the freezing point of water. These 0 points are arbitrary and can be set anywhere, so they don't representing the absence of thermal energy. That means temperatures on these scales can go below 0 or above, depending on the situation. Here's the key. The size of 1 degree or 1 Kelvin is the same in terms of thermal energy change. For example, a change of 1 degree Celsius equals a change of 1 Kelvin. But because their starting points differ, the actual temperature values are not directly comparable in an absolute sense. If you increase the temperature by 10 degrees Celsius, it's the same thermal change as increasing by 10 Kelvin. But 0 degrees Celsius does not mean no thermal energy, while 0 Kelvin does. This difference matters a lot in thermodynamics, which is the study of heat and energy. Many equations and laws relying on temperature being measured from absolute zero. For instance, the ideal gas law, which relates pressure, volume, and temperature, uses Kelvin because it reflects the true energy content of the gas particles. If you used Celsius or Fahrenheit, the calculations wouldn't be accurate because those scales don't start at the physical limit of zero thermal energy. In practical terms, scientists and engineers prefer absolute temperature scales when doing precise work. Whether designing engines, studying chemical reactions, or calculating energy changes, using Kelvin or Rankine ensures the numbers match the real energy states of particles. Relative scales like Celsius and Fahrenheit are still useful for everyday weather reports or human comfort, but they aren't suitable for the fundamental calculations that depend on true thermal energy. So, to sum it up, temperature intervals are not absolute values because the 0 points on different scales are set differently. Absolute scales begin at a physical limit called absolute zero, making their measurements directly related to the energy of particles. Relative scales use convenient reference points that don't reflect the true energy state, so their 0 points are arbitrary. This distinction is why scientists relying on absolute temperature scales for accurate thermodynamic work.